speaker is Maharnoosh Rufi. She is a PhD student at University of Pittsburgh, in the final year of her program. She is advised by Dr. Yutao Zhang, and her research mainly lies in hardware security and memory systems. Her thesis primarily revolves around enhancing the efficiency of secure memory with the ultimate goal of facilitating its widespread adoption. She is currently in the job market and looking for an opportunity to join the industry. Please, Dr. Rufi.
Hi everyone, I'm from the University of Pittsburgh. Today I'll be presenting our work EP-ORAM, efficient NVM-Friendly path selection for ring-ORAM in hybrid memory. Privacy is a major concern when outsourcing data in cloud computing. Imagine users accessing a cloud server that provides CPU processing like Intel SGX. In that case, CPU is trusted, but everything off-chip is untrusted, including memory bus and memory modules. Therefore, an adversary can snoop on them and infer sensitive information, potentially. Users can store their data encrypted, so data content itself is safe, but address is transmitted plain text in commodity DRAM. Therefore, the memory access pattern can leak sensitive information to the adversary. To achieve the highest level of privacy, encryption is not enough. Access pattern also needs to be protected. The question is how to protect access pattern. Recent studies tell us to use ORAM, which is a cryptography to obfuscate memory access pattern. At the memory side, there is an ORAM structure that keeps user data blocks randomly reshuffled in the memory. At the CPU side, there is an ORAM controller that translates one block request to many block requests. For example, user requests block A and many blocks are returned. We call that the adversary can snoop in the untrusted domain, but in this way cannot recognize what block actually the user intended to access. ring-ORAM is one of the most promising ORAM protocols that has been proposed in the literature. Compared to other ORAM protocols, ring-ORAM requires reading less number of blocks from memory per user request. So it is faster and consumes less bandwidth. But here is the catch. It has a very large space demand, 4.8 times of the actual user data. So that is why in this work, we aim to address this high space demand problem of ring-ORAM. Let us take a closer look at this matter. If we use DRAM while adopting ring-ORAM to protect the access pattern, on one hand it is good because DRAM is fast, but on the other hand, DRAM is a precious and a limited resource, and this high space demand of ring-ORAM will practically waste most of it. And if we use NVM entirely, we'll have a higher density than NVM, so high space demand of ring-ORAM is less of an issue. However, NVM is slow, and this exacerbates the ORAM performance overhead, which by the way is high. And besides, NVM has a limited write endurance, while ORAM incurs a lot of memory writes. So that's why we proposed EP-ORAM in an attempt to have the best of both worlds by introducing an efficient hybrid design. Before we can dive into EP-ORAM design, we need to know about ring-ORAM basics. Ring-ORAM is a tree-based ORAM protocol in which memory blocks are organized in the form of full binary tree, and each node is a bucket that can contain a number of blocks, and each user block is randomly mapped to a path in this binary tree. And less than 50% of the ORAM tree contains user data blocks. The rest are filled by dummy blocks. So this extra space of dummy blocks is there to help with the security promise for the reshuffling, and also in Ring-ORAM specifically, there's a performance reason for that. And each user request reads one block per level, and there are maintenance write operations to basically refresh the Ring-ORAM tree. Let's see how Ring-ORAM works through an example. To access block A, we first need to find out the path that block A is mapped to, for example, path 0. Then we need to find out what bucket along the path actually has block A. And then afterward, we will read one block per bucket on path 0. One bucket returns A, and the rest of them just return a dummy block. And at the last step, we basically invalidate whatever we have read. So eventually, bucket will run out of valid blocks. And by the way, the block that we have read needs to be remapped to another path. So we don't want to read the same block from the same path. For these reasons, we need to have a write operation. And that's why Ring-ORAM has two write operations. We have bucket reshuffle, which is rewriting an entire bucket, reading it, reshuffling it, and writing it back. It is on demand. And then we have path eviction, that is rewriting an entire path. Unlike bucket reshuffle, this one is statically scheduled after every 5 normal Ring-ORAM accesses. We have one path eviction, and paths are chosen in a predetermined order. So as you can imagine, path eviction accounts for the majority of memory writes in Ring-ORAM, as it writes the entire path. So that's why in this group we focus on optimizing this operation. Now let's take a closer look at Ring-ORAM bucket organization in order to better understand the root cause of its high space demand. So a portion of block are designated to user data. Half of this purple space across the tree can have contain the actual user block. The rest needs to be dummy. And there is another portion, this one is dedicated to dummy blocks only. For the performance reason, the more reserved dummy blocks we have, the less buckets we reshuffle. So it's better for the performance. So if we calculate the overall utilization across tree, it is only 21%, or in other words, as we mentioned before, Ring-ORAM needs a space of 4.8 times of the user data. So however, this is the overall utilization. A particular bucket may have a different utilization at a given time. And that is why we studied bucket utilization more closely. We made a key observation regarding the bucket utilization across the Ring-ORAM tree different levels. So as you can see in this figure, buckets at middle levels are significantly underutilized, meaning most of the time they do not contain any user data. So we explored the underutilized middle levels to design a more efficient path eviction operation for our hybrid setting. So here's our design. Binary theory capacity grows exponentially. So it is only natural that in a hybrid memory, we store the top levels in DRAM and the bottom levels in NVM. Here, the K-last levels are stored in NVM. In the baseline, a pass eviction affects an entire pass, which we call full pass. But in EP-ORAM, we propose to have also short pass eviction, which only affects the first edge levels, such that levels in NVM experience less number of accesses, meaning less number of write operations. So ideally, we want many short passes and a very few full passes eviction. However, in order to preserve ORAM security guarantee, the pass accesses needs to be indistinguishable. So the pattern should be fixed, always issuing M short passes followed by N full passes. And you can imagine with short passes, user blocks tend to stay longer at middle levels, meaning at the end of the short pass actually. And this is feasible, this is doable because as we saw earlier, middle levels had low utilization. So, introducing short pass evictions actually has two benefits. First of all, EP-ORAM can save more levels in NVM with a comparable performance, as a result saving more DRAM space. And second, EP-ORAM reduces the number of memory writes on NVM, therefore improving NVM write endurance. And here is our evaluation methodology. We use a trace-based simulation and spec CPU 2017 as our benchmarks. We implemented the ring-ORAM with 24 levels as the baseline. This is the result for DRAM space saving. As you can see, the ring-ORAM baseline, the purple bar, where all levels are stored in DRAM, will require 12 gigabytes of DRAM space, which by the way, only 2.5 gigabytes of it is usually, the rest is the dummy space needed for ring-ORAM. If we store two levels in NVM in a naive hybrid design without any further optimization, we can reduce this DRAM space demand to 3 gigabytes. But with our design, EP-ORAM, the green bar, we are able to save 3 levels in NVM with comparable performance and reduce DRAM space to 1.5 gigabytes, which is compared to the naive hybrid design, EP-ORAM saves 50% of DRAM space. And here we see the result of EP-ORAM reducing the number of NVM writes compared to the naive baseline by 15% on average. And regarding the middle level utilization, EP-ORAM makes better use of middle levels, and that is why short pass evictions are doable. And finally, here is a takeaway. To achieve full user privacy, we need ORAM to hide access pattern. ring-ORAM is a promising ORAM protocol, but has high space demand. DRAM and NVM hybrid memory can benefit a ring-ORAM space issue. But saving more levels in NVM causes a slowdown and a write endurance problem. And that is why we propose EP-ORAM, an NVM-friendly ring-ORAM that is able to save 50% of DRAM space and reduces NVM writes by 15 compared to a naive hybrid setting. Thank you very much, and I'll be happy to take questions at the question section.